All right, so we're going to be looking at page 251, number 10. So here's page 251, number 10. It says, suppose the edge lengths x, y, and z of a closed rectangular box are changing at the following rates. So they just tell you straight up what the rates are. Sometimes we have to dig that out a little bit. They're telling you dx dt is 1, dy dt is negative 2, dz dt equals 1. And I'm going to find the rates of several things. The volume, the surface area, and the diagonal length are changing. So the rate at which the volume is changing is a little tricky, the very first one that we're going to look at here. But it's not the problem that's tricky, it's the derivative. We'll have a look at that. So we want to know the rate at which the volume is changing. So if we follow our system, collect all the given information recording rates of changes ddt. Note decreasing quantities get negative ddt. Create variables for unknown quantities. Sometimes that's going to be important. For this one, we don't need to create any variables. We've got all the variables we need. It's x, y, and z. You don't need any more than that. All right, so just adjust my lamp a little bit here because it's looking pretty stark. All right, there we go. So when we've collected all the information, but what I like to do as part of my information collecting is collect what the question is. So here's our collected information for step 1. And they give us something else. I think they need to give us something that refers to a specific time. It says, at the instant when x equals 4, y equals 3, and z equals 2. We're always going to have something like that. So that goes with our collected information up here. It's telling us that x equals 4, y equals 3, and z equals 2. And then the other thing we want to put as part of our collected information for part A is the question is, what is dA dt? All right, so I've collected all my information. The next thing that I'm supposed to do is write an equation relating the variables of the problem. Sometimes that's difficult to do. In this case, it's easy because it's just volume. So volume equals x, y, z. Now, unlike optimization, here I'm not bothered by multiple variables because I'm differentiating implicitly. And that's what implicit differentiation was designed for, was to handle multiple variables. So that's set up all nicely. So now I'm ready to do step 3, which is differentiate implicitly. All right, so I already write an equation. I already did that. Differentiate implicitly with respect to t. All right, so if I do ddt on both sides, all right, so the derivative of volume, all right, so you can think of it like this. The derivative of v is 1, and then because I'm doing derivative of v with respect to t, it's 1 dv dt. Or I can just say the derivative of v is dv dt. Now, here's where it gets tricky, because this is a product, so we should use product rule, but it's a product with 3 factors, and we've never done that. So how are you going to do it? Here's how we're going to do it. We're going to break this up into, we're going to basically consider this to be f and this to be g. All right, so we're going to separate out yz as a single function. And then we'll apply our product rule, and then when we go to do g prime, we'll just have to use product rule again. All right, so our product rule is f prime g plus f g prime. I'm probably going to run into that, but okay. My f prime is, so what is f prime? It's 1, but it's dx dt. Don't forget, because you're doing a derivative of x with respect to t. So the derivative of x is dx dt. And then I have to go times g, which is yz. All right, and then I have plus the function f, just x, because I'm not doing a derivative, so it doesn't get a dx dt. But now I have to do g prime. All right, how am I going to do g prime? G prime is a product rule, so it has its own product inside of it. So we're going to have another f and g. The red f and red g. I've got green f and g and red f and g. This is for Christmas time, okay? So when I go to do my g prime, all right, it's going to have f prime g plus f g prime. So what are those going to be? You can think about that ahead of time if you want. F prime is going to be dy dt. G is just z plus f, which is y, g prime, which is going to be dz dt. There you go. All right, now let's see what we can sort of simplify this as. So we're going to get, I'm going to put all the variables in front and the ddt's at the end. Yz dx dt plus, if I distribute out the x, xz dy dt plus xy dz dt. So you might notice a pattern here. I've got my three variables in my product, and I just took the derivative of one of them each time. So it's like you start to see that the product rule that you learned is sort of a special case, and you could develop, it's sort of fun to do, a general product rule for n factors. It's pretty interesting. Anyway, that's what we got by just using the product rule twice is the other way you can do that. Okay, so now let's answer our question. What is, oh, I'm sorry, I wrote dA dt, but this is dV dt, wasn't it? It said find the rate of change of volume. A doesn't stand for volume. Or we could find the rate of a volume. No, it's V for volume. dV dt, that's, I wrote it here, and I didn't write it right up there. All right, so anyway, dV dt is what we're looking for, therefore we're not going to put in a value for it, but we can put in a value for all the other stuff. By the way, I was going to say a little bit about what this box is doing. Like, how is this in any way meaningful? So you have, like, what's going on up here? dx dt equals 1 means the x direction, the box is expanding upward at a rate of 1 unit per time unit. What are our units here? Is it centimeters and seconds? Probably should know that. Let's see, our units are, oh, it's meters per second. Okay, so this thing is expanding upward at 1 meter per second. The y is compressing at 2 meters per second. So the y direction is going in, right, at 2 meters per second. And the z dimension is expanding at 1 meter per second. 1 meter per second. So basically what you have is this box that is being squished in at the same time it expands up and out. So you could think of this either as like, this is a block of metal that's trapped inside a vise and is being squished this way so that y and x directions are expanding to compensate for that. Another important application of something like this is in climatology and meteorology. What we usually do to study the motion of air is we'll break a mass of air into little cuboids, to borrow Nathaniel's word from before, cuboids. I like that word actually. So we'll break the air mass into cuboids, but those cuboids are not static. They're like expanding and contracting. Their moisture level and temperatures are changing, and they're moving in space and time. All right, so they're just doing a lot of things that we have to keep track of, and then we just throw all these little packets into a supercomputer and have that calculate where things are going to be, 2 days from now. Did I say something else about that? Can't remember what. Oh, and then the size of the cube that you start with is essentially the resolution of your program, and then the more cubes you use, the more computations you have to do, but the more accurate your outcome. And it's one of the reasons we want quantum computers, is that they will be able to do many orders of magnitude more calculations per second, so we'll be able to model the climate better and know better about how much time we've got left. All right, so that's just some kind of discussion about what's going on in this box. Now, this box, by the way, does not have a constant volume. So it's not like a block of metal that's static. It's changing in volume. Otherwise, the dV dt would be 0. So as this box gets skinnier and taller and deeper, its total volume is changing. That's why the air mass is sort of a better application of this than a block of metal. But you could imagine a block of metal that changes volume as well because it's being compressed. All right, so let's plug in values. So we know what y and z are. They're 3 and 2. So for yz, let's just put 6. Our dx dt we know is 1. Our xz is 4 times 2 is 8. Times our dy dt is -2. Our xy is going to be 4 times 3, which is 12. And then our dz dt is 1. All right. So what do I get? -16 plus 12 is -4 plus 6 is 2. 2 what? 2 cubic meters per second. Volume is cubic meters. Time is seconds. And that makes sense because I'm talking about how fast is volume changing and per unit time. This cuboid, this rectangular prism, is changing its volume at a rate of 2 cubic meters per second. So it's getting larger, 2 cubic meters per second. If the dV/dt were negative, then the volume of the box would be decreasing, it would be shrinking. This volume of the box is expanding. Happens a lot with, gas packets. So for example, the temperature could be increasing, the volume could be expanding, or the density could be decreasing, volume could be expanding. All right, we'll look at the other parts next.